I can begin two ways. I can give a recap of what we did the last time and then take questions, or take questions first. Anybody have any preference? Well, meanwhile, let me at least get the page. I'll go back to Zoom. Share screen. Ability. Okay. So maybe a quick recap, and then I'll take questions if anybody has any homework questions. We talked about the binomial distribution. And if X is a number of successes, probability that X is K just turned out to be nothing more than, and choose K, P to the K, Q to the N minus K, where N is the number of trials in the experiment. P is a probability of success. We also showed that the moment generating function is P e to the T plus Q raised to the nth power. Please don't memorize this fact. It's all given to you in the table in the text, which I'll provide you on the exam. And the expectation turns out to be very simple. N times P. The variance turns out to be N times P times Q. That's sort of a summary of the binomial expansion. The binomial has a property. Every trial can be classified as success or failure. They're all independent trials. Every time you do the experiment, it's independent. And the probability of success on every trial is the same as P. That's crucial. Then I talked about the hypergeometric, which was really not new. The way I defined it is I said, suppose there are R red marbles, and the remaining marbles are some other color. And we choose N without replacement. And the probability that X, on X, oh, hold on, I have to do my X. And X is equal to the number of red. Then the probability that X equals K, meaning from the R red, we choose K. From the N minus R, we choose N minus K over and choose little n. And I didn't prove it. It was just messy algebra. I do it in the text. That if we let R over P, how do I define R over N equal to P? If we define this, then the expected value, the expected number of red would be N times P, and the variance is a little different. It's N P, I don't remember what it is. There's an N minus N and N minus 1. Let me look it up. Hypergeometric, it's NP, N minus N over N minus 1. something you don't want to memorize. And then I went to the next distribution, which was the geometric distribution. That is the probability that, again, for the geometric, X is the first success. We're assuming everything is independent. And the probability that the first success occurs on the K plus is just Q to the K minus 1 plus B. And we showed for the geometric that E of X is 1 over P. V of X is was it a P over Q, was it? I don't remember. I don't remember. I don't see why you have to remember. Q, it's Q over P squared. I'm sorry. And the interesting thing also, by the way, is the moment generating function, which I showed you how to get the other day. It turns out to be P e to the T over 1 minus Q e to the T. You'll check these right in the text. These are all very important distributions. They come up a lot in probability theory. The geometric in particular, we've done the geometric before when we talked about geometric series. Problem number 2 on your exam was really a geometric distribution. Now, I then talked about the negative binomial, also called the Pascal, distribution. And what that asks is, what's the probability that the mth success occurs, say, on the kth trial? Or I think I said or the kth success occurs on the nth trial. I don't remember which notation I used in the text. It doesn't make a difference. The interesting thing here is, and I didn't prove this the other day, I think I gave you the results, but what's interesting about the Pascal is, for example, suppose we want to know what's the probability that the 5th success occurs on the 10th toss. And I showed you it's an easy problem to do. In the first 9 tosses, you get success, and in the last one, you have to get a success. So basically, it's a binomial, the product of a binomial and a simple probability. But it turns out, if you think about it for a second, let's suppose, for example, you wanted the kth success. That means what you could do is you could take the Pascal, define x of I to be the number of trials between the ith and the I plus first success. And that becomes geometric, because now we're talking about a single trial. Because then what happens is for the Pascal, what happens is the expected value, you just get m over p. For the variance, you get mq over p squared. And for the moment generating function, you just get an m up here, an extra power, the same inside. Because the Pascal is just a generalization of the geometric. I don't know how often it comes up in any applications of Pascal, but if somebody asks you a simple problem, it's easy to do. For example, suppose you toss a coin a coin. Determine probability. The fifth head occurs on the ninth toss. And I'm assuming the probability of the head is a half, okay? Well, if the fifth head is going to occur on the ninth toss, that means in 8 tosses, you have to get 4 heads. And on the last toss, you get a head whose probability is a half. In 8 tosses, if you wanted 4 successes, the problem is easy to do. Okay, so that's a recap of the distributions I discussed up until now. Did anybody have any questions about any of the homework exercises so far? It's awfully quiet. How about a problem like number 20? 10 sharpshooters fire simultaneously at a target. Assume that each sharpshooter has an 85% chance of hitting the target. And we're assuming that no sharpshooter affects anybody else. The problem determine the probability the target is hit at most twice, or it's hit. Okay, so let's look at this. Shooter. Okay, I lost the place. This was, I said, number 20. Okay, number 20. I have 10 sharpshooters. Assume each has an 85% chance of hitting the target. Determine the probability the target is hit. Well, if the target is hit, that means it's hit at least once. Let's let X equal to the number of hits. So the question is, in order for it to be hit, what's the probability that X is greater than or equal to 1? This is clearly a binomial experiment, by the way. And by the way, this is just equal to 1 minus the probability that X is 0. This is a binomial. There are 10 sharpshooters, and we want no successes. The probability of success is 0.85. This would be 1 minus 10 to 0, 0.15 to the 10, whatever that turns out to be. So that was a pretty simple problem to do once you recognize it was a binomial distribution. Then I give, let's look at number 18. A bag contains 6 red and 4 blue, otherwise identical marbles. And we're drawing 4 without replacement. X is equal to the number of red. Y equals to the number of blue. Determine the probability that X equals 3. Well, that's not hard to do. That's a simple hypergeometric. There are total 10 marbles and you're drawing 4. If you want to get 3 red from 6, then you need 1 blue from 4. And that would give you your answer. And there's more to the problem, but it's very simple. Does anybody have any particular questions you want me to talk about? I don't know what's disturbing you. All right. And you guys have to be aggressive and ask questions. All right. So I want to talk now about Pascal, where is it? The Poisson. So if you remember the last time, I gave you 2 results. I said the limit of 1 minus lambda over n, the nth power, as n goes to infinity, is equal to e to the minus lambda. And power series, x to the n over n factorial, as n goes from 0 to infinity, happens to equal to e to the x. And this fact comes from calculus 2. Okay. Now, I'm going to be using these facts along the way to prove certain things are true. But so let's just store this for future reference. Okay. The Poisson distribution. First, I can define it, and then I can just tell you how it actually comes about. X is said to be a Poisson distributed random variable with parameter lambda greater than 0 if the probability that x equals k is equal to lambda to the k e to the minus lambda, I'm sorry, e to the minus k. E to the minus lambda to k. E to the over k factorial, where k takes on any non-negative value. One can actually prove that the sum of all these probabilities, this infinite series converges, and it gives you 1. The sum of all the probabilities is 1. And I do that for you right in the text. So this is the Poisson random variable. Now, this comes up in lots of applications. Maybe I'll tell you now. For example, things are Poisson distributed if, for example, if you look at the number of stars in a given volume of space, you look at the number of misprints on a book. Errors of that type usually occur with a Poisson distribution. In fact, I'm going to show you in an example very shortly that the Poisson distribution can be, the binomial distribution can be approximated by the Poisson distribution. So again, I want to develop the moment generating function for the Poisson distribution. So the moment generating function, remember, would be e to the kt, which is the sum of e to the kt times the probability that x equal k going from 0 to infinity. Now let me put this in. I can take out the e to the minus lambda. And now I have e to the kt lambda to the k over k factorial. Let's look at this a little bit more closely. And I have e to the t lambda to the k over k factorial. Now, if you go back to this expression, what I have is x replaced by lambda t, e to the t lambda. So this becomes e to the minus lambda. And then this becomes e to the t. Oops. Oh, let me write that better. Oops. E to the t. Oh, this is e to the lambda. This just becomes e to the lambda, this becomes e to the lambda, e to the t. Or, oops, e to the lambda times. The problem is I don't want my glasses on, I can't see what I'm doing. E to the t minus 1. Okay, so the moment generating function for this random variable turns out to be e to the lambda, e to the t minus 1. Now, if you compute m prime of 0, I'll do it for you in the text. Okay, so you compute m prime of 0, it will turn out to be lambda. And double prime of 0 will turn out to be, I don't remember what it turns out to be. And double prime of 0 turns out to be, well, let's say it this way. So E of X turns out to be lambda. And using n double prime of 0, we find that V of X is also lambda. So we have, for the Poisson distribution, an interesting result. Probability that X equal to K is lambda to the K, e to the minus lambda over K factorial. V of X and E of X both equal to lambda, and that comes from the moment generating function. So we have a pretty interesting result. And now we're going to show you something else which is also interesting, namely that you can approximate a binomial distribution by a Poisson. So that means I'm going to claim the following. Okay, a binomial distribution with parameters n and p can be approximated by a Poisson distribution with NP equal lambda. And that's what I'm about to prove. Okay. So let's start with the Poisson. Let's start with the binomial distribution. Probability that X equals K is equal to n choose K P to the K and Q, which is 1 minus P, the n minus K. And I'm going to prove that as I'm going to look at this as n goes to infinity, meaning for large n, we can approximate the Poisson distribution by the binomial. Now, many of you may just accept this, but we're mathematicians, and we need to show that this is true. So what do we do? Well, actually, you can actually do this another way too. You can do this with the moment generating function as well. Okay. So I'm going to replace P with lambda over n from here. So if I do this, I'm going to get n minus 1, n minus 2, all the way down to n minus k minus 1. over k factorial. I'm just working out the combinations. And now times p to the k becomes k over n to the kth power, and 1 minus lambda over n to the n minus k power. Okay, so we want to play with this. So let's write this a little differently. I have lambda to the k, that's this time. And I have a k factorial. I have 1 minus lambda over n to the n, that's coming from here. I have n minus 1, all of these, n minus k minus 1 over all these k terms over n to the k. And there's a times 1 minus lambda over n to the minus k. Now, remember, n is going to infinity. Well, if n is going to infinity, this term stays. That's just lambda to k over k factorial. We know this becomes e to the minus lambda. That's a definition, one of the definitions of e. And all of these terms go to 1. Because we have k of these. So we see that the limit as n goes to infinity of the binomial can be approximated by a Poisson. Okay. So that's the Poisson distribution. And let's look at an example or two. Okay, and I'll show you how we can use the binomial approximation if we wanted to. Okay, so if we look at the example I give you the text, I say, suppose on the average, 2 phone calls a minute. Arrive at a switchboard. Switchboard is the way the phones used to work. Determine the probability of no calls arriving during a 5-minute interval. Well, if 2 calls arrive per minute in a 5-minute interval, we have 10 calls, right? So lambda would be 10. So the probability that let's say that we get no calls during this, x is the number of calls. We get no calls during this time interval, would be lambda to the k e to the minus lambda over k factorial. And we want k to be 0. So this is just e to the minus I can't read my own handwriting. Where are my pluses? E to the minus 10. So once we recognize what lambda was, the problem becomes very simple. I do it a little differently in the book, by the way. Now let me show you about the binomial. Suppose 1% of all bulbs are defective. In a sample of 100, determine the probability 2 are defective. Well, this is really a binomial distribution. If X is the number of defective, from 100, we're choosing 2. 1% are defective. And if you work this out, it's 0.1849. However, if we have lambda equal n times p, which is 100 times 0.01, which is 1, and if we use a Poisson distribution, we get 1 squared over 2, e to the minus 1, and the answer turns out to be 0.1839. So notice, approximating a problem by Poisson might be easier to do than actually doing it via the binomial distribution. That was the whole point of this exercise, to show you that we can approximate binomial distributions by Poisson distributions. There's one more distribution I want to talk about in this section. I mean, there's all the stuff I talk about, but just in case you come across this. So let me begin with an example.
Okay.
A fair number is tossed 21 times. Determine the probability of obtaining a 1 3 times. Where did I lose my place? A 2 4 times. A 3 2 times. A 4 once. A 5 6 times. And a 6 5 times. So basically, I would let x1 be the represent the number of times a 1 would appear, x2 would be the number of times a 2 would appear, x3 the number of times a 3 appears, and so on. Now it turns out that the solution to this problem is trivial. It turns out it's a generalization of the binomial distribution. And I'm just mentioning it in case you come across it. I'm never going to ask it. So what's happening is There are 21 outcomes. Of these 21 outcomes, you want a 1 3 times, you want a 4 2 times, you want a 3 2 times, you want a 4 once. Hold on. I'm saying it wrong. So I want a 1, here it is. I want 1 1, 4 2s, 2 3s, 1 4, 6 5s, and 5 6s. Of course, these numbers are up to 21. And then I would get for each of these the probabilities I have.
Oh, Professor.
Yes.
The first digit on the bottom of the combination is a 3, not a 1.
Which one?
The one on the bottom in to the far left is a 3.
Thank you. Thank you, John. Now, each of these, I want 3 of these. I want 2 of these. So notice this is just a generalization. So I want 4 of these of the binomial. I want a half, 2, I want a half, or the number of successes for each one. I want a half, 6, a half. Yeah. That is, one can generalize a binomial if there are more than one success. In this case, we have different kinds of successes. So I just mentioned this in passing. Okay, this concludes what I want to do in this section, 2.12. And it includes discrete probability. And now I just want to talk a bit. So you can finish any problems you like that I've assigned in section 2.12. So now I need you to remember your calculus. And let me tell you why. The basic notion we studied in probability for discrete probabilities is we work with sums, the sum of the probabilities. The sum of all the probabilities is always equal to 1. Now, you might recall that when I looked at histograms, if I represented these as histograms, you could think of probabilities being the area of each of these rectangles. So one could interpret, if one wanted to, a probability as a histogram. Even though these were discrete outcomes, one can still use a histogram and then use the notion of an area and think of the probabilities just being the area under that particular rectangle. Well, things are a little different now. We all took calculus, and we all remember that in calculus, the generalization of a sum is an integral. So an integral, for example, an integral from a to b of f of x dx, if f is a non-negative function, can represent the area of this region. And we all have that in our basic calculus course. And you all remember how to do some basic integrations. If you don't, please remember, you're going to need it in doing some problems. So for example, if you needed to integrate x to the n power, if n is not equal to -1, if n is equal to -1, remember it's a logarithm. So one should remember how to integrate. One should remember the derivative of the exponential function. This will show up a lot. It's pretty straightforward. The derivative of any polynomial is pretty straightforward. Sometimes you got to be a little bit clever in doing an integration. For example, suppose you want to integrate let me do it this way. Oh, nope, that's not good either. It's a 4. This would be 5. Suppose you wanted to do this. Remember that? So here there was a substitution method. You would let 5x plus 4 equal to u. du is equal to 5 times dx. This becomes u to the 1/2. dx becomes du over 5. And the limits change when x is 0, u is 4. When x is 1, u is 9. And then you integrate. And that gives you an answer ultimately. So you may need to be able to do these things. So if you've forgotten how to integrate, please review. No fancy integration, just basic integration. Now, why is all this important? Have my time. Okay. Because now we want to talk about continuous random variables. Up until this point in the course, we've been talking about discrete random variables. Now, by a continuous random variable, we mean a random variable whose range is an interval or a union of intervals. What do I mean? Suppose I'm talking about the lifetime of a light bulb. And suppose I know every light bulb can last up until 600 hours. Well, then the range could be any number between 0 and 600. You can take on any value. So in this case, the interval would have been 0 to 600. Okay. So let me talk some more. Now, I just want to talk generally. I'm not ready to do too much just yet. So how do we deal with continuous random variables? Well, let's suppose I have the following function. So I have this triangle. And this triangle describes some particular random variable. And you'll see how it comes about soon enough. First thing I want to observe is, what's the area of this triangle? Well, base is what? Base is 1. Height is 2. The area of the triangle is 1/2 the base times the height, which is 1. The way we deal in the discrete case with the sum of all probabilities equal 1, when we deal with continuous random variables, the total area underneath the curve must be 1. Sometimes we call that normalization. You don't need to know the word. We have to talk about areas 1 because we're going to be talking about probabilities. So in fact, we're going to define a special function called a probability density function. PDF, not a portable document format. Okay. And it has the property that it's a non-negative function. And the total area under this curve, A and B could be infinity and minus infinity, must be 1. So we're going to discover, let's go back to this example I had a minute ago. If I'm going to want the probability that we lie within this region, it'll just be the area of this curve divided by the area of the entire curve. So we're going to define the probability. Oops. That A lies between X, between A and B, where X is the random variable, to B, the area under this curve sometimes I can put a little subscript here, but I don't really need it here because it's clear I'm only talking about one random variable. So this represents the area under the curve. And now this leads you almost immediately to an interesting observation. What's the probability that X equals A? Well, that would be the integral from A to A, right? From A to A? What is the integral from A to A? What's the integral from A to A? It's 0.
0.
0. That means for a continuous random variable, probability that X is a particular value is 0. Notice in the discrete case, that's the impossible event. This is not impossible in a particular case. It's possible that a light bulb might fail at exactly 2 hours, but its probability would be 0. Now, I want you to observe that for a discrete random variable, we have P of X of I is always a number between 0 and 1 for all xi, and the sum of all the probabilities of all possible I equals 1. For a continuous random variable, f of x is always greater than or equal to 0, and the total integral from A to B, and A and B, A could be minus infinity and B could be plus infinity, okay? Of f of x dx. The total area under the curve, which is called the PDF, remember, probability density function is 1. The CDF is f of x equal to p of x less than or equal to x. That doesn't change. Oops. For the continuous case, we'll have f of x is the probability of minus infinity up until x of f of t dt. Where this is a sum, this is also a sum. Actually, it's an infinite sum. E of x will be summation x of I, p of x of I. What's going to happen in the continuous case f of x dx and v of x hasn't changed. So all the ideas that we had before are the same. Now, let me just give you one more example. How am I doing time? Okay. The continuity, when I talk about a continuous random variable, when I talk about continuity, I'm talking about continuity with respect to the range. It's possible for the function itself not to be continuous. For example, consider the following function. F of x equal x. X is between 0 and 1. 0 and 1 and 2. 1/2 between 2 and 3. And 0 elsewhere. So let's look at this graph. Here's 1, here's 2, here's 2. So x is equal to between 0 and 1. Okay. Between 1 and 2, 0. It's 1/2 between 2 and 3. And elsewhere it's 0. Okay. So I draw a slightly different version of this picture on page 136, 176 in the back, wherever this is. What page is it? Yeah. But notice this is a discontinuous PDF. By the way, show it's a PDF. This area is 1/2. This area is 0. This area is also 1/2. But the total area under the curve is 1. So this could represent a probability density function. Now, in the same way, by the way, I didn't mention it, we can define the moment generating function. The moment generating function is e to the tx, which in this case would just be the integral from minus infinity to infinity of e to the tx f of x. Yeah. So all the ideas that we had for a discrete random variable automatically come over to a a continuous random variable. Let me just remind you one more result. The CDF I really just want this before. This is the CDF. Remember in calculus that if you take the derivative of an integral, you get the integrand. Which means given the CDF, what happened there? Given the CDF, you can always recover the PDF by taking the derivative. That's just an observation. Okay, so what I want you to do is I want you to read very carefully section 3.1. You'll finish up the homework in section 2.11, but I want you to read section 3.1. I will walk through a bunch of examples the next time. I'm going to do some very, very important continuous distributions. In particular, I'm going to do the exponential and the uniform continuous distributions. Okay, so I'm going to stop at this point. Let me wish you each a really good Thanksgiving. And remember what I said earlier, Gordon's law is save room for the dessert. Anybody have any particular questions? Let me take control of the screen. Okay. Anybody have any questions? Please do the homework exercises. These problems aren't hard. And if they're bothering you, the only way I'll know is if you ask me and I'll work them out for you. Over this weekend, I hope to work out your exam again and I'll send it to you so you have a solution. Okay, anybody have any other questions?
Professor?
Yes.
I just have a quick question. So, last example, like you did with 1% of, I just have a question. If, so you did this like with two different formulas. So it's not always works, right? With like to do it by
A lot of problems you can do many different ways.
Oh, okay.
Yeah. That is, you can always think of lambda, some people think of lambda as a function of time. You don't have to, but you could. I like to think of it as a function of time.
Okay, thank you.
Okay, Nadia? Anybody else?
Okay.
Questions? Okay, folks. So enjoy your Thanksgiving.
Thank you, you too, Professor.
You too, Professor. Enjoy your Thanksgiving.
Okay, and remember, the desserts matter. Okay, let me close off shop.